Welcome to the video lecture on concavity and the second derivative test. In this lecture, we're going to learn what the second derivative can tell us about the graph of a function. And we're going to start by talking about something called concavity. Concavity is like the curvature of a graph. This first graph is what we call concave up, and it looks like your typical valley shape where you have sort of this minimum going on, and then this shape over here is called concave down, and this looks like your typical hill shape where you're going down the curve. When you talk about concavity, what you're going to notice is that it has something to do with the second derivative. If we sketch in all of our little tangent lines to this concave up graph, we'll have a zero tangent line right where that minimum is, and then we have all these other tangent lines going on. If you look at where the zero slope is, to the left of that we have some negatively sloped tangent lines, and to the right of that we have positively sloped tangent lines. As we read through this graph from the left to the right, these tangent line slopes are starting out negative, a little less negative, a little more less negative, then it hits zero, and then it's slightly positive, a little more positive, a little more positive, and so on as these tangent lines get steeper and steeper. So what happens is that these slopes, which are also known as the first derivative, are increasing in size as we go from left to right, because they're going from negatives through zero and up through positives that are getting larger and larger. So these derivatives, these slopes, are increasing. And if a function is increasing, that means its derivative is positive. So if f prime represents these slopes and those slopes are increasing, then the derivative of those slopes, the derivative of those derivatives, which is actually going to be the second derivative, needs to be positive. So concave up is going to happen when we have a second derivative that is positive. What you'll also notice from this graph is all of these tangent lines that I drew lie below the actual curve itself. So the graph of the function lies above its tangent line. And the opposite of that happens when we do concave down. So if I draw in all of these little tiny tangent lines, every single one of these tangent lines lies above the actual function itself. And what you'll notice is that right here's your zero slope. To the left of it we've got positives, and they're getting more and more positive as I go to the left, and as I go to the right these slopes are negative and they're getting more and more negative as I go to the right. So I start with a big positive, a slightly less big positive, and so forth until I hit zero, and then a little bit negative, a little bit more negative, and a little bit more negative as I continue on. So as I go from left to right, I'm passing through positives down to zero and down to more negatives. So those slopes, or those derivatives, are getting smaller this time. They're decreasing. And in order for a function to be decreasing, its derivative needs to be negative. So in order for these f primes to be decreasing, their derivatives, which would be the second derivative, needs to be negative. So a graph will be considered concave down if it has a negative second derivative, which is the same as saying its first derivative decreases. So here's our formal definition. Suppose that f is a function whose derivative f prime exists at every point in an open interval I. Then we say that f is concave up on that interval if f prime is increasing. So if these slopes are getting bigger. We say that f is concave down on that interval if those slopes, or those derivatives, are decreasing. And those definitions imply our next test for concavity. So if f prime is increasing, that means its derivative, which would be the second derivative, needs to be positive. So if the second derivative is positive, greater than 0, then we say that the function is concave up. And if we want f prime to be decreasing in order to be concave down, then the derivative of f prime, which would be f double prime, needs to be negative. So if f double prime is negative, then your original function f will be concave down. So concave up is this typical U shape, concave down is that typical hill shape. Now when we make our graphs, what we're going to see is that every single graph is made up of 4 possible scenarios. And by piecing together these 4 different shapes, creates every possible graph that would be out there. So these top 2, if you joined them together, would form that hill shape. So these are both concave down. The difference between them is that this shape on the left is an increasing graph because it's rising up. So this would be the situation where you have a function that is concave down and increasing, versus this piece over here, which is also concave down, but now the graph falls. So this would be the situation when you want to be concave down but decreasing. These two on the bottom form that valley shape, so they are both concave up, but the one on the left falls, so that would be decreasing and concave up, and the one on the right rises, so that's increasing and concave up. Okay, so we're going to figure out a test and a strategy for figuring out which of these 4 pieces we want our graph to have, and we're going to piece them all together to create the entire graph. Now, if a graph is concave up, will it have a relative max or a relative min? Well, think about concave up. Concave up is this U shape, so that obviously has a relative min at the bottom. So if we are concave up, then we potentially are going to have a relative min. If your graph is concave down, that's that hill shape, so that is going to potentially have a relative max. So this is called your second derivative test. It's just an alternative way to determine whether or not you have a relative max or a relative min. And remember, we already have a first derivative test that we can use to determine if you have a relative max or min. So this is just another alternative that is sometimes easier to use than the first derivative test. So this is what the first derivative test says. Suppose that you have a function f for which the derivative exists for all x in an open interval contained in its domain, and that there is a critical point c in that interval for which the derivative is 0. Okay, so you have to have a place where the derivative is 0, not d and e, but the derivative needs to be 0. If that happens, then f of c will be a relative minimum if the second derivative is positive. And the reason why is because if your second derivative is positive, that means you are concave up. You are that U shape, and that's why you're going to have a minimum at that particular critical point. If your second derivative is negative, that means you need to be concave down. So if you have a critical number where the derivative is 0, then that critical point has to be a maximum. That's the only kind of extrema you can have if you're concave down. This test will fail if the second derivative is 0. And if that happens, then you're going to have to fall back on that first derivative test instead. Notice that you can only do this second derivative test if the first derivative is 0. If the first derivative is d and e, then the second derivative will also be d and e, and you wouldn't be able to apply this second derivative test. Okay, we're going to practice this in just a little bit. Now, another thing that's very important that's determined by looking at second derivatives is something called a point of inflection. A point c, comma f of c on the graph of f of x is called a point of inflection if the following conditions are satisfied. First of all, your function f needs to be continuous at c, so you can't have things like asymptotes or holes or something like that. Number 2, there has to be an open interval a comma b containing that c such that the graph is concave up on the left and concave down on the right, or vice versa. So you have to change concavity in order for there to be a point of inflection at this point C. So you have to have a change of concavity. And then the third requirement is that you have to have a tangent line to the curve at c comma f of c. So this does not allow for the possibility of having a derivative that is d and e. It has to be something where the derivative actually exists. Okay? So here are 4 different examples of what a point of inflection would look like. This first one is kind of like an S shape, and the reason why it's a point of inflection is because this point in the middle, where that center point is, that's your point of inflection. To the left of it, we have that concave up shape, and to the right of it, we have that concave down shape. So we have that change in concavity. We go from a second derivative that's positive to a second derivative that's negative. Over here, again, this middle point is called your point of inflection. To the left of it, this is considered concave down, so your second derivative would be negative, and to the right, this would be concave up, so your second derivative would be positive. Again, change in concavity. In this situation, we are concave down on the left because we're falling and decreasing and having that hill shape, and then to the right of your point of inflection we're back to concave up, and over here we start out concave up on the left and then we go to concave down. So these are the 4 different shapes you might see when you have a point of inflection, and they all have a different type of concavity on the left versus the right. If the second derivative changes sign at this number c, and if there is a tangent line at that point c, then it will be considered a point of inflection. To find these, what we're going to do first is find possible points of inflection, which I sometimes call PPI, and these are going to occur wherever that second derivative is 0 or where that second derivative is d and e. That doesn't guarantee that it's going to be a point of inflection. You have to actually test your possible points of inflection and make sure that a change in concavity actually happens and that tangent line needs to exist at that point. In other words, that first derivative needs to exist. Okay? So again, we will practice all of this. Let's summarize all of our strategies for curve sketching. This is a very important part of calculus, being able to use what the first and second derivative tell us about a function to be able to sketch a graph of the curve without the use of a graphing calculator. You should be able to do all of this by hand. So the very first thing we're always going to do if we're being asked to sketch a curve is find our first derivative and our second derivative. We're going to find the critical points of f prime, and those are going to be the places wherever that first derivative is either 0 or d and e. Then we're going to find similar points for the second derivative, so where that second derivative is 0 or d and e. Then we're going to make a number line for f prime, putting those critical points on there, and we're going to make a number line for f double prime, putting its critical points on there. Then we're going to test each interval and put in our pluses and our minuses for both the first derivative and the second derivative. So you're going to have a first derivative number line and a second derivative number line. And you're going to line those number lines on top of each other in order, just like this, and you're going to have your different critical numbers, whatever they happen to be. So suppose I have C1 here and C2 here. Now what the first derivative test tells us from this number line for the first derivative is where I'm increasing, where I'm decreasing. If you see any plus signs on this first derivative number line, then that's where your graph will increase. If you see any minus signs, then that's going to be where your function decreases. If you see a plus followed by a minus going up and then down, that's your relative max. If you see a minus followed by a plus, so that you go down and then you go up, that would mean that you have a relative min. So this first derivative number line will always tell you where you increase, where you decrease, and where you have relative maxes and mins. And that was called that first derivative test. Now we're going to do exactly the same thing for the second derivative, but using those critical numbers for the second derivative. And if you see any plus signs on here, then that's going to tell you where your original function is concave up. And if you see any negatives on this second derivative number line, those are the intervals where your original function will be concave down. In order to have a point of inflection, you would need to see a change. So either plus then minus or minus then plus, and those would be your points of inflection. If you see plus plus or minus minus, then it will not be a point of inflection. Now once you find all of these things, then you're going to need to find the y values of all the important points, like your maxes, your mins, and your points of inflection. And you can always find your y values by going back to the original function f and plugging in the x value. Then you're going to plot all of those. Plot your maxes, plot your mins, plot your points of inflection, plot your x and y intercepts, and any other points that you might find necessary. And finally, using your number lines, you're going to determine whether you want your graph to be concave down, increasing or decreasing, or concave up, decreasing or increasing. And it's going to be one of these four possibilities. And then you're going to piece each of those shapes together to get the entire graph. Okay? So let's do a typical example. We're going to find all of the important information about this cubic function. We're going to find all the intervals where it increases, decreases, where it's concave up, where it's concave down. We're going to find the coordinates of the relative maxes and mins. That's what relative extrema means. We're going to find any points of inflection, and then we're going to put it all together into a sketch of a graph. Okay, so step number one. Always find your first and second derivatives first. So the first derivative would be 6x squared minus 6x minus 12. And our second derivative would be 12x minus 6. Now you want to find the critical points of your first derivative and the corresponding critical points of the second derivative, because those are going to be the things that we put on our number lines. So we would need to find out where this is 0 or d and e. And since this is a nice quadratic function, it's never going to be d and e, but it will equal to 0. I have a factor of 6 throughout, so let's pull out our 6. And if I factor what's left, I'm going to need an x and an x, a 2 and a 1, and I'll need the 2 to be minus and the 1 plus. So that means I'm going to get a 2 and a negative 1, and those are called our critical numbers for the first derivative. So over here, on my first derivative number line, I'm going to have negative 1, and I'm going to have 2, and I'm going to go ahead and write down next to this that factored form, 6, x minus 2, x plus 1. And we're going to need to test each of those. I will do that in a minute, but let's go back and do exactly the same thing, but for the second derivative. So we would need to find out where the second derivative is 0 or d and e. Now this is a nice linear function, so it's never going to be d and e, but it will equal to 0. If I set it to 0, we're going to get x is equal to a half. So we're going to put that on a number line as well. My second derivative was 12x minus 6, and a half, you want to make sure you line it up in order with or in reference to that first derivative number line. So a half would be somewhere in between negative 1 and 2. So make sure you line it up correctly. Now that we have our number lines, we're ready to test. Now when you do your test points, you're testing it into that particular derivative for that particular number line. So for example, if I want to figure out what sign I want over here, I would need to test something less than -1, say -2. So if I plug in a -2, 6 is obviously positive, -2 minus 2 will be negative, and -2 plus 1 is negative, so two negatives make a positive, so this will be plus. If I test something in between -1 and 2, I could try 0. 6 is positive, 0 minus 2 is negative, 0 plus 1 is positive, so this middle region will be negative. And if I pick something bigger than 2 like 3, 6 is positive, 3 minus 2 is positive, 3 plus 1 is positive, so we're back to plus. Okay? Now we're going to do the same thing, but this time we're going to be testing into the second derivative because we're doing our second derivative number line. So I need something smaller than a half, say 0. 12 times 0 is 0. 0 minus 6 will be negative. So this is minus. And if I pick something bigger than a half like 1, 12 times 1 is 12. 12 minus 6 is 6, so that's positive. Okay? So now that I have all of those signs filled in, we can answer these first 4 interval questions. Where do I increase? Well, that is determined from your first derivative number line. You will be increasing on this original function whenever its first derivative is positive. So this interval here would be minus infinity up to -1, and also this interval here, which is from 2 to infinity. And where I see the minus sign is where the original function decreases. So that would be from -1 up to 2. Notice that I'm using parentheses around all of those endpoints. Okay, so increasing and decreasing is determined from your first derivative number line. Concave up and concave down come from your second derivative number line. Concave up is where you see plus signs on your second derivative. So that would be this interval here, starting at a half and going to infinity. Again, use parentheses. Concave down will be wherever I see minus signs. So that will be the other side from minus infinity up to a half. Okay? Now, to find relative mins and maxes, you can use that second derivative test. But usually when I'm doing these problems where I'm making my number lines and I'm going to be making my sketch, I've already done all the work to create this first derivative, so it's just as easy for me to look there using that first derivative test to figure out my maxes and my mins. Since this goes up on the left because it's increasing and down on the right because it's decreasing, this is going to be a relative max. And at 2, I go down on the left because I decrease, and then I go up on the right because I increase, so that's going to be my min. So we will have a relative min at 2 for the x, and a relative max at -1 for the x. I will figure out what those y values are in a little bit. Let's go ahead and find our points of inflections first. So to find points of inflection, you go over to your second derivative number line and you're looking for the change in concavity, which means you need a change in signs. And since I do go from a minus to a plus, then this is going to be or have as a result a point of inflection. So my point of inflection will be when the x is 1/2. Now in order to find these y coordinates, we want to always go back to our original function right here. This is always where you find your y's. Now I'm not going to do all of them for you, but I'll show you, for example, -1. That one's easy enough to do by hand. So to figure out the y coordinate when x is -1, you would just plug in -1 for each of these x's. So that would be 2 times -1 cubed minus 3 times -1 squared minus 12 times -1 plus 8. A negative cubed stays negative, so this will be -2. A negative squared becomes positive, but I have that minus in front of the 3. Minus 12 times minus 1 is plus 12. So this is going to be 20 minus 5, which is 15. So doing that same process for the other 2 points, if I plug in 2 instead, we will get negative 12. And if I plug in 1/2, we end up getting 1.5 or 1.5. And you can just do that on your calculator. Okay? All right. Now what we're ready to do is piece it all together to get our graph. So let me erase this to make some room. The way we're going to get our graph is we're going to use these number lines to help us. And what I like to do is take an imaginary, and sometimes I even draw it in, vertical line right through every single critical point on the first derivative number line and the second derivative number line. So I want a line through -1, a line through 1/2, and a line through 2. And that's going to create 4 different regions where I'm going to have those 4 different shapes. Now remember what our shapes look like. These are the 4 possibilities. The bottom 2, whoops, sorry about that. The bottom 2 are concave up, and the top 2 are concave down. This one on the left increases, this one on the right decreases, this one on the left decreases, this one on the right increases. So we're going to go over here and we're going to figure out which of these 4 shapes we're supposed to have. So wherever I see plus signs on my first derivative, that means I increase. So this means I'm increasing here and here, and that means I'm decreasing here and here. Wherever I see pluses on my second derivative, I want to be concave up. So that's everything bigger than 1/2. So this region would be concave up, and this region would be concave up. Where I'm minus, which is everything less than 1/2, I need to be concave down. So concave down, concave down. So which of these 4 pieces is both concave down and increasing? That's this one right here. So I want that shape until we hit -1. Then when I get to -1, between -1 and 1/2, I still want to be concave down, but now I want to be decreasing. So that's this half over here. So I want to have that shape where I left off, and I'm going to do that shape until I hit 1/2. Then between 1/2 and 2, I want to be concave up, decreasing. So concave up, decreasing is this shape down here in the lower left. So I'm going to do that shape where I left off until I hit 2. And then after 2, I'm concave up, increasing. So that's the other half of that U shape. And I'm going to pick that up where I left off. And I don't make any further changes afterwards or before that -1, so you're going to have arrows on those 2 ends. So that's essentially our graph. The only thing we need to do now is place it correctly on our grid. So what I'm going to do is make my graph, and I'm going to plot all of my key points, which would be my mins, my maxes, and my points of inflection. And if we need to, we may not need to, but we could also put in some intercepts and any other additional points that we find necessary. So I'm going to plot 2, -12. So that would be right about here. -1, 15. So that would be right about here. And then 1/2, 1.5. Now that's not a whole lot of points, it's only 3. So if you go back to your original function, you could find some intercepts. Now finding the y-intercept when x is 0 should be really easy to do. If you plug in 0 for these three x's, you'll just get that 8. So we know that we will have a y-intercept at x equals 0 and y equals 8. So I know that I'm going to cross this y-axis at 8. 1, 2, 3, 4, 5, 6, 7, 8. So there'll be a dot right there. To find the x-intercept is a little harder to do, because then you would let 0 be y on this side and you'd have to try and solve that, and that doesn't look very easy for me to do, so I'm not going to bother. Only do it if it's easy. Okay? So now that we have some points, we're going to take this shape and replicate it so that it goes through these points. Now remember, -1 was that little maximum, and that's this dot right here. So we were supposed to rise up to that max. So I'm going to rise up to that max, and then between -1.5 and this dot right here is my 1/2, we're going to finish off that hill shape. And while I'm doing that, I'm going to pass through my y-intercept. So this is going to come down and hit that 1/2. And then after 1/2, I'm going to change to concave up until I hit that minimum at 2. So we want to go concave up until we hit our 2. And then after 2, we're going to finish that U shape and just go up from there. And then I can put my arrows on. And there's my graph. Okay? We'll practice this some more in just a little bit. Okay, so here's my next example. Here I want to take the function 5x to the 2/3 minus x to the 5/3. And I'm saving us a little bit of work here by already telling you what the first and second derivative are simplified. Sometimes that will be given to you, sometimes it won't. It just depends on the problem. If it wasn't given to you, then you would have to take your derivative, and you'd probably have to do a little bit of factoring and cleaning up in order to get these nice two derivatives. So it's a little bit of work. That's why I'm giving us the answer already. Okay, so once we have our two derivatives, we're ready to go ahead and figure out what our critical numbers are going to be. So that's going to be wherever this derivative is 0 or d and e. Now, because it's a fraction, this could potentially become undefined and become d and e whenever that denominator is 0. And in this case, that denominator will equal to 0 when x is just 0. So this happens when x is 0. The numerator equaling 0 will happen and cause the whole fraction to be 0. So in order to find out when this whole fraction is 0, just look at where the top is 0. And you can see, because it's already nicely factored, that that's only going to happen when this 2 minus x is 0, which happens when x is just 2. So that's kind of why we want it in this nice factored form, so that you can just look at it and see exactly where your zeros are going to be for the top and for the bottom. If we do that for the second derivative, this numerator will be 0 when x is just -1, and this denominator will be 0 again if x is just 0. Okay, and that's going to be the d and e case right there. So we know all of our critical numbers. We're ready to put them on our number line. So my first derivative is this 2 minus x over 3x to the 1/3. And my second derivative is this -10, 1 plus x over 9x to the 4/3. Make sure that you're labeling these derivatives so you know which one is which. And on my first derivative number line, I want to put 0 and 2. And on my second derivative, I want to put -1, which would be somewhere over here, and 0 as well. Okay, so there's my two number lines. Now what I want to do is fill in my pluses and my minuses. So we're going to need to do some testing. So let's start with that first derivative. Let's test, say, -1. So if I test -1, 5 is obviously positive, 2 minus a negative 1 is actually 2 plus 1, so that's positive. And a cube root, which is what a 1/3 power is, of a negative stays negative. So the bottom will be minus, which means this whole quotient will stay negative. So we're going to have a big minus sign to the left of 0. Okay? Now let's test positive 1 in the middle here. So the top will be positive for the 5. 2 minus 1 is positive, and the cube root of 1 will be positive. So that is now going to be plus. Okay, and then let's take our last interval here and try, say, 3, something bigger than 2. 5 will be plus, 2 minus 3 will be negative, and cube root of 3 is going to be positive. So the whole fraction will be negative. All right, so now we have our signs for that first derivative. Let's do the same thing for the second derivative. So we need to test something less than negative 1, say negative 2. Negative 10 is negative. 1 plus negative 2 will be negative. And negative 2, a cube root of that would stay negative, but this power on top is a positive 4. That's an even power, which means anything you raise to an even power is going to become positive. And when I multiply that by a positive 9, that means this denominator is always positive no matter what I plug in. So that bottom is a plus. 2 minuses become plus, so this is going to become positive. If we try something in between negative 1 and 0, maybe like negative 1/2, I'll get a negative from the 10. 1 plus negative 1/2 is positive 1/2, so that's plus. And remember, that denominator is always positive no matter what. So now I'll only have one minus sign, so this will be minus. And finally, if I test something like 1, negative 10 is negative, 1 plus 1 is plus, and the bottom stays plus always. So this will stay negative. Notice there's no change in signs right there. Okay? So we've got all of our positives and negatives filled in, so that means we should be able to fill in where we increase, decrease, concave up, and concave down. And these are looking for intervals of these. So, first derivative number line. Wherever you see a plus sign is your intervals of increase. So 0 to 2. Wherever I see minus signs are my intervals of decrease. So that's going to be minus infinity up to 0, union 2 to infinity. For concave up, wherever I see plus signs on the second derivative is where I will be concave up. So that's going to be minus infinity up to that negative 1. And concave down will be wherever I see minus signs. Now technically at 0, we were not concave up or down because it was one of those critical points. So I'm going to leave it out. So I would write my concave down as negative 1 to 0, union 0 to infinity. Depends on the instructor and the book. Sometimes I've seen this written as just negative 1 to infinity, but I personally like to leave the 0 out because it was a critical point. Okay? Now, from this first derivative and the first derivative test, I can tell my maxes and mins. This goes down on the left because it decreases, and then up. So this is a min. And this goes up on the left and down on the right. So this is a max. Then we can tell from our second derivative number line that we have changes in concavity resulting in points of inflection. So at negative 1, I do go from a plus to a minus, so this is going to be a point of inflection, whereas at 0 it did not change, so that will not be a point of inflection. Okay, so 0 will not be anything in this example. So let's fill those in. We have our relative min at 0 for the x, and our relative max at 2 for the x, and our point of inflection was -1 for the x. So to find these y values, we would go back to this function. If you plugged in 0 into that, you would obviously get 0 back again. So this y value would be 0. If I plug in 2, I'm going to get a bunch of decimals. So you would need your calculator for that. And if you plug it in, it turns out to be approximately 4.76. And if you plug in -1, -1 cube root stays -1, but then we square it. So this becomes +5. And -1 here, I take its cube root, it stays negative. I raise it to the 5th, it stays negative, but then I multiply this by this minus sign, so it becomes plus. So this is 5 plus 1, so that means this y coordinate would be 6. And you can do that on your calculator as well. All right, we've filled out our list. Now we're ready to make our graph. So I always like to do sort of a rough sketch over here based on my number lines. I'm going to clear out some of this information, and then I put it together on the actual grid. So remember how I do this. I put little dashed vertical lines through every important critical number. So -1, 0, and 2. And this creates 4 different intervals. Wherever there are minus signs on that first derivative, that's going to be decreasing. So this is decreasing less than 0. So both here and here is decreasing. Then I switch to increasing, and then I'm back to decreasing. On the second derivative, wherever I see pluses, that's concave up. Wherever I see minuses, that's concave down, and it's minus for every other region. So all 3 of these are concave downs. And then I have my 4 possibilities. These are both concave down. These are both concave up. This is increasing, decreasing, decreasing, increasing. So on this first region, I want to be concave up and decreasing. That's this shape right here, and I want to have that shape until I hit -1. Then between -1 and 0, I'm now concave down, decreasing, which is this shape over here. So I want to start this up at the top and then go down. So I'm going to start this at -1 and then go down to that 0. Then between 0 and 2, I want to be concave down, increasing. That's this shape over here. So I want to start at 0 and then I have to arc up. And you might think that looks a little strange there at 0. What do we call that? That's called a kink or a cusp in our graph. And that usually happens when we have a derivative that does not exist. And that is exactly what that 0 represented. That was when that first derivative was dne. So that's exactly what our graph should look like. We do want to have a kink or a cusp in our graph right at 0. So this is looking good so far, and we're doing that until we hit 2. And then after the 2, we want to be concave down, decreasing. Concave down, decreasing is this shape right here. And we continue that till the end, so put arrows on your end. All right, so now we're just going to replicate that graph on my grid with actual points that I go through. And I'm going to use my mins, my maxes, and my points of inflection. So 0, 0, 2, 4.76. Just estimate where that would be. And then -1, 6. All right, now we piece it together. We already had our y-intercept that was 0, 0, and our x-intercept at 0, 0, so I don't have any other intercepts or points that I could add to this that would be easy to find. So let's just use these three and hope that we have enough information to get our graph. Now we're going to this first dot on the left, that was -1, and I wanted to kind of come down into that point. Just like that. Then I'm going to arc down into 0. And that's where we have that cusp. So then we're going to arc up to this 2. And then after 2, we're going to arc back down. And we have our nice max at 2. And we have our nice min at 0. And we have our point of inflection at -1 because we are concave up and then concave down. So there's my graph. Okay? So these are time-consuming problems. You have to be very, very careful. You have to be especially careful getting your pluses and your minus signs right, because if you screw those up, it's going to completely alter the shape of the graph and the correct pieces that you should be using. So you have to be really, really careful. All right, so let's take a tiny bit of a break from that and let's talk about this second derivative test for a moment. We haven't really used it at all yet, and I want to show you how it is used and how it can be helpful. So suppose that you are given a function like this cubic function right here, and you are asked to find the relative extrema. So the normal way we would do that, and the way we've done on the previous two examples, would be to take the derivative, 6x squared plus 6x minus 12. It's never going to be d and e, but it will equal to 0. And we can find that by factoring out a 6 and then factoring that trinomial. And we would get x and x, 2 and 1. This would be plus and minus. This should be a 2. And if we set those to 0, then we get -2 and +1. So those would be called our critical numbers. And what we would normally do is we would then put those on a number line. And then we would test our intervals. So if I tested something like -3, then this would be +6, -3 plus 2 is -1, -3 minus 1 is -4, so two minus signs become plus. And then if I tested 0, then this would be a plus, 0 plus 2 is plus, 0 minus 1 is negative, so this would be minus. And if I tested 2, it would be plus, 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 so this would be plus. And then what that number line would tell me is that I go up and then down. So I have a relative max at -2, and then I go down and then up, so I have a relative min at 1. Now if I was going to be graphing this function, and that was what the problem asked me to do, then I would go ahead and do this process of finding that first derivative, because you're going to need that information anyway in order to make your graph. So why not use what you already have? However, if the question only asks you to find the maxes and mins and it doesn't ask you to graph, then there's a shorter, faster, easier way, and that's to use this thing called the second derivative test. So the second derivative test still requires you to find these critical points. So you still need to take that first derivative, set it to 0 or d and e, and solve for x. But now what you do is you take your second derivative, which here would be 12x plus 6, and then what you're going to do is plug in each of those critical numbers into the second derivative. So I am going to take my second derivative and I'm going to plug in -2. So 12 times -2 would be -24, and -24 plus 6 is less than 0. That'll be a negative answer. Now if your second derivative is negative, that means you are concave down, which means you're that hill shape. What kind of extrema would you have to have if you're concave down? You have to have a max right up there at the top. So this means we have a relative max at -2. Then I would take my second derivative and I would plug in 1. So 12 times 1 is 12 plus 6, that's a positive. So that means we're concave up. And if you're concave up, the only kind of extrema you could have would be a relative min, because you would be that U shape. So without doing number lines, without testing every single interval, I'm just testing these two numbers and that's it. But I'm testing them into the second derivative. If you get a positive answer, you'll be a min. If you get a negative answer, you'll be a max. So that's how the second derivative test works. It saves you a little bit of time, but I usually only use this method if all I need to know is if I have a max or a min. If I have to do other things like graph, then I just stick with my first derivative test. Okay, so let's try another example like that. So here my function is x e to the negative x. So in order to do this, we're going to take our first derivative because we need to know those critical points. Those are going to be the only places where I'm going to have relative maxes or mins. So that requires taking a derivative. Now the derivative here, be careful. This is x times e to the negative x. That means you need a product rule. So we're going to do the first times derivative of the second plus the second times derivative of the first. So the first would be x times the derivative of the second. Now the derivative of e to the stuff is e to the stuff right back again times stuff prime. And the derivative of negative x is a negative 1. So there's first times the derivative of the second plus the second times the derivative of the first, and the derivative of x is just 1. So this is negative x e to the negative x plus e to the negative x. Now with these e problems like this, what I usually do is factor out that e to the negative x, and that's going to leave me with a negative x plus 1. So this would be the same as 1 minus x. I'm just switching that order around to make it look a little bit nicer. And then I'm going to take that e to the x and flip it down to the bottom. So then I can easily see where this is going to be 0 and where this is going to be d and e. It's obviously going to be 0 when the top is 0, which happens when x is 1. To find out when it's d and e, that would be when the bottom is 0. Now think about the graph of e to the x. E to the x is an exponential growth graph like this. When does this graph hit 0? It doesn't. It's asymptotic. It gets closer and closer to it, but it never actually hits. So this doesn't happen. So the only critical number that I have is at 1. Okay, so now that I know that, what I'm going to do to apply my second derivative test is take the second derivative and then I'm going to plug in 1 and see if I get a positive or a negative. So let's go ahead and do our second derivative. Now this was my first derivative right here. Or you could use that fraction version of it. Either way, either you're going to do a quotient rule if you're doing a fraction, or you're going to do a product rule. I'm just going to stick with my product rule. So this would be the first times the derivative of the second. The derivative of negative x plus 1 is negative 1. Plus the second times the derivative of the first. And the derivative of e to the negative x is e to the negative x times negative 1. Now let's clean that up. We're going to get a negative e to the negative x. And here we're going to get a negative e to the negative x times a negative x. So that actually becomes a positive e to the negative x. And then we're going to get a negative e to the negative x times 1. So that'll be staying negative e to the negative x. Oops, I forgot my x in here. Okay, so I just took my negative 1 times e to the negative x times our negative x, so it became plus, and we have an x and an e to the negative x left, and then my minus e to the negative x times 1. Okay, so simplifying that, these are like terms, so we'll have a minus 2 e to the negative x plus x e to the negative x. If you want, you can factor out that e to the negative x again, and you'll be left with a minus 2 plus x. Okay? Now once we have that second derivative, what we're going to do with it is we're going to plug in our critical number. That's how the second derivative test works. You take this second derivative and you plug in that critical number. So if I plug in 1, this becomes e to the negative 1 times negative 2 plus 1. All we care about is the sign. So e to the negative 1 is like 1 over e. That's like about a third. That's positive. And negative 2 plus 1 is negative 1, so that's negative. A positive times a negative is going to stay negative, which means if your second derivative is negative, you are concave down, and the only kind of extrema you can have if you're concave down is a max. So that means we have a relative max at this critical number, x equals to 1. Okay? So the second derivative test can be a little bit of a time saver because you don't have to draw all those number lines, but it's still a little bit of work since you're going to have to calculate both your first and second derivative and do some plugging in. All right? Okay, let's try one last example, and this will involve a trig function. Okay, so we've got the function 2 sine x plus cosine 2x. So in order to apply the second derivative test to this, we still need to find that first derivative test and find those critical numbers. So the derivative of 2 sine x, the 2 would stay there, and sine x becomes cosine x when you do its derivative. Then the derivative of cosine 2x, you need a chain rule on that because you've got a cosine and you've got that 2x. So the derivative of the cosine part would be minus sine. This is going to be minus sine of that same 2x. And then we'd have to multiply that by the derivative of 2x, which is just a 2. So I'm going to put that in front. So there is my first derivative. Cosine and sine are always nicely defined. They're never fractions or anything like that. So we don't have to worry about dividing by 0. We just need to find out when this will be equal to 0. We don't have to worry about the d and e case. Now in order to solve this, what I would recommend is changing this sine 2x into that double angle identity. And what you have to remember from some trigonometry is that sine 2x becomes 2 sine x cosine x. That's the double angle identity for sine. So this is 2 cosine x minus 4 sine x cosine x. So to solve this, I can factor out a 2 cosine x. That'll leave me with 1 from this term minus a 2 sine x from this term. And then if I set each of these to 0, if I take 2 cosine x and set it to 0, I don't need to worry about the 2 because I could divide by it. When does cosine of x hit 0? Well, on the interval 0 to 2 pi, cosine is 0 at pi over 2 and 3 pi over 2. Okay, so that's two critical numbers. Now let's take this second factor and set it to 0. So I would add that 2 sine x over, and I'm going to get a half. When does sine of x equal to a half? Well, that's going to be at our pi over 6 angles, and we want them in quadrant 1 and quadrant 2 because sine is positive in quadrant 1 and 2. So the pi over 6 angle in quadrant 1 is just called pi over 6, and in quadrant 2 it's 5 pi over 6. So our four critical numbers are going to be pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. So now to find out whether those are maxes or mins, you could either put them all on a number line and then test every single interval, which is going to take a little while, or you can use the second derivative test. So that would require taking the second derivative and then plugging in each of these values. So to do the second derivative test, I'm going to take the second derivative and I'm going to choose to do it from here because that's going to avoid having to do a product rule on this part over here. So I'm going to take my derivative from the very first line. The derivative of 2 cosine x. The 2 would stay there, but the derivative of cosine x is minus sine x. And then the derivative of minus 2 sine x, the minus 2 will stay there. The derivative of sine 2x is cosine 2x times the derivative of the 2x, which is a 2. So simplified, this second derivative becomes minus 2 sine x minus 4 cosine 2x. Okay, so now we are ready to do our plugging in. If we plug in this first critical number, pi over 2, into this second derivative right here, we're going to get a minus 2 times sine of pi over 2. Sine of pi over 2 is 1. Minus 4 times cosine of 2 times pi over 2. 2 times pi over 2 is pi. Cosine of pi is negative 1. So we're going to get a minus 2 plus a 4, which is 2. And since that's positive, that means we're concave up, so we're that U shape. That means we have a minimum. Okay, so now we go to 3 pi over 2. So we get negative 2 times sine of 3 pi over 2 is negative 1, minus 4 times 2 times 3 pi over 2 is 3 pi. Cosine of 3 pi is negative 1. So we'll get 2 plus 4, which is 6. That's still positive, so we still have a min. Now we go to pi over 6. We'll get negative 2 times sine of pi over 6 is that 1/2, minus 4 times 2 times pi over 6 is pi over 3, and cosine of pi over 3 is positive 1/2. So we get negative 1 minus 2, which is negative 3. Now we're to a negative, which means we're concave down, so this is a max. And finally, if I plug in 5 pi over 6, we're going to get minus 2. We're going to get positive 1/2 again, minus 4 times cosine of 5 pi over 3. 5 pi over 3 is in quadrant 4. I had to think about that for a moment. Quadrant 4, and cosine is positive in quadrant 4, so this will be a half, and we'll get the same thing that we had before. So we'll have negative 1 minus 2 is negative 3, so that's a max. So time consuming, but it's still going to be the same amount of time or longer to do your number line. Okay? All right. The next example is a little bit different. This time what we have given to us are just a bunch of characteristics of a function, and we want to put it all together and create a graph that has all of these characteristics. So we want f of 0 to equal f of 2, and those both need to equal 0. So think about what that means. That means you want the point 0, 0 on your graph and 2, 0 on your graph. So immediately we know 2 points to plot, 0, 0 and 2, 0. That's what that tells me. Then I'm told that f prime of x is greater than 0, which means positive, if x is less than 1. F prime of 1 is equal to 0, and f prime of x is less than 0 if x is greater than 1. So let's put these three things on a number line. Now the fact that f prime of 1 is 0 means it's a critical number. So we have a critical number at 1. And when we're less than 1, that derivative was positive. So that means we have a plus sign. And if we're greater than 1, then that derivative was less than 0. So we have a minus sign. So it's telling me where I'm increasing and decreasing. And it's also telling me that I have a maximum right at 1. Okay? Now we're going to put that information together with the second derivative that they tell me. They tell me that the second derivative of this function is always less than 0, and it doesn't give me any conditions. So if you think about your second derivative number line, that means it's always minus everywhere. Okay? So let's put this information into a sketch, and I'm going to do it by drawing in those imaginary vertical lines, and I actually only have one here right through 1, where I see plus signs on my first derivative, I'm increasing. Where I see minus signs, I'm decreasing. And on my second derivative, if I always am negative, that means concave down. So both of these will be concave down. And if you think about our 4 pieces again, our 4 options, these are my 2 concave down options. These are my concave ups. This increases, decreases, decreases, increases. So over here, I want to be concave down, increasing. That's this upper left corner. So I want to have that shape until I hit 1. And then after 1, I want to be concave down, but decreasing. So I have to fall like that. So here's 1, right in between these 2 points, I need to be rising up to that little maximum at 1, and then after 1 I fall down and I go through those 2 intercepts, and that's all that it tells me. There's no other critical numbers to change any behavior, so we can just stick our arrows on the end, and there's my graph. So this would be the sketch of a graph that satisfies all of these conditions. Okay, let's go ahead and do another graph. This time I want to sketch the graph of x over x squared plus 1. And again, I'm going to save us a little bit of time here by telling us the first and second derivatives already simplified and solved for. Otherwise, you'd have some pretty nasty quotient rules to do with some factoring, and it would take you a little bit of time to figure those out. So here's my first derivative. Now, if you're going to be sketching a graph, then you always want to find those critical numbers of your first derivative, which are going to be wherever this is 0 or d and e. And because that top is already nicely factored for us, it should be real easy to see where that numerator is going to be 0. So that's going to happen at plus and minus 1. Now the denominator equaling 0 would be wherever this whole fraction is d and e. So is it possible for that denominator to equal 0? No, it's not, because if you set x squared plus 1 equal to 0, you're going to have to try and take the square root of a negative number, which can't happen. So this is impossible. We don't have to worry about that case. Okay? Let's go ahead and find our critical numbers for the second derivative. So we're going to find out where that numerator is 0, and we're going to find out where the fraction is d and e. So the top, again, is nicely factored. Where this x is 0, we will get a 0 in that numerator. And where this whole factor is 0 will give us another solution. So where does 3 minus x squared equal to 0? If I add that x squared over and take a square root, remember that you get plus or minus when you take a square root. So we're going to get a plus or minus square root of 3. And then in the denominator, again, x squared is always positive. So when I add 1 to that, this is always going to be greater than 0. It's never going to equal 0. So this is impossible again. Okay? So now that we have all of our critical numbers, we're ready to go ahead and make our number lines. Okay, so I'm going to label my first derivative and my second derivative. For the first derivative, we have -1 and +1. And if we test our points, notice that that denominator is always squared. So this denominator is always going to be a positive value. So if I tested something like -2, 1 minus -2 becomes positive, and 1 plus -2 is negative, and that denominator is always plus. So this will be minus. If I test 0, 1 minus 0 is positive, 1 plus 0 is positive, and the bottom is always positive, so this will be plus. And if I test 2, 1 minus 2 is negative, 1 plus 2 is positive, and the bottom is positive, so this will be minus. Okay? Now let's go to our second derivative. We have -√3, which is a little bit bigger than -1, so this is going to be to the left of -1, and +√3 will be to the right of +1. And we also had 0, so I'm going to put 0 in there as well. And now we need to test all of these different places. So in the bottom, notice we have a cube. However, x squared is positive always. And when you add 1 to that, it's going to stay positive. And that positive cubed will stay positive. So again, the denominator is always going to be positive. We don't even need to bother testing it at all. It's just the numerator that's going to determine my sign. So for example, if we tested something less than the negative square root of 3, like maybe -2, okay? Then -2 times -2 is +4, and -2 quantity squared becomes +4, and 3 minus 4 will be negative, and that bottom is always positive. So overall, this will be negative. Now if I test something like -1, -2 times -1 is positive. 3 minus -1 squared is 3 minus 1, which will be positive, and the bottom is always positive. So this is plus. If I test +1, -2 times 1 is negative, 3 minus 1 is positive, and the bottom is plus, so we're back to minus. And finally, if I test something like 2, -2 times 2 is negative, 3 minus 2 squared, or 4, will be negative, and the bottom is plus. So this is back to plus again. All right, let's draw in our lines. So we're going to have a little line through -√3, a little line through -1, a line through 0, a line through 1, and a line through √3. I had minus to the left here, so this is decreasing and decreasing, and then I was plus between -1 and 1, so this is increasing, increasing, and then I went back to minus again, so decreasing, decreasing. Then for the second derivative, my minuses were concave down, so here, here, and here, and my pluses are concave up, so here, here, and here. And here's my 4 choices. Up, down, down, up. So on this furthest point on the left over here, we want to be concave down, decreasing, so that's this upper right corner, until I hit -√3. Then between -√3 and -1, I want to be concave up, decreasing. So that is this shape right here. So we have a point of inflection right at -√3. Then between -1 and 0, I'm concave up increasing. So that's this shape right here. So I have a minimum right at -1. Then between 0 and 1, I'm concave down increasing. So that's this shape. So I have another point of inflection at 0. And then from 1 to √3, I'm concave down decreasing. So that's this shape. So we have a max at 1. And then after √3, we're concave up decreasing. So that's this shape right here. So we have another point of inflection at positive √3. So this is my general shape. All I need to do now is position it so that it goes through the right dots that I need it to go through. So we're going to need to find some coordinates. Our key points are all of these critical numbers that we have. So -1, +1, -√3, 0, and positive √3. And you're going to be plugging those back into this original function. So if I plugged in -1, I'd get -1 over 1 plus 1 or 2. So this is -1/2. If I plug in +1, I'm going to get 1 over 2 or +1/2. When you plug in -√3, I would just go ahead and get a decimal for that. That's about -0.433. When you plug in 0, you'll just get 0. And when you plug in +√3, you get +0.433. So let's plot these 5 points. So -1, -1/2, +1, +1/2, -√3, -4.33. So that's just a little bit higher than the one we had before. I'm exaggerating it a little bit there. Let me lower it just a tad. Whoops, erased a little bit too much there. So here was -1. -√3 would be a little to the left of that, and -0.433 is a little bit higher than our -1/2. So it's going to be somewhere like right there. And then 0, 0, and then √3, which would be about here, and 0.433 is just a little lower than our half. So something like that. Now we're ready to connect the dots here. So we want to come down into that first dot on the left. So this is going to come down into this point. Then I change concavity, and then I curve up to my 0, and then I curve up to my max at 1, curve down to my √3, and then I switch concavity just like that. So there's my graph, and you will have a little bit more accuracy with your pencil than I do on my computer here with my pen, but it should have these general curvature shapes to them on our graph over here, and mine's a little bit sloppy because of the inaccuracy that I have with my pen, but hopefully you get the idea. Let's try another one. Okay, sketch the graph of this function x²⁴ minus x². And again, I'm giving you the two derivatives already. So let's start by finding the critical numbers. So we need to find out where this numerator is 0 and where this denominator is 0 to give me the D and E case. Now 4 minus 2x², that's going to equal 0. If I add that over and divide by 2 at plus and minus √2. So this is going to give me x equals plus or minus the square root of 2. And this denominator will equal to 0 when 4 minus x² equals to 0. And that is obviously going to happen at plus or minus 2. So we have lots of critical numbers for that. And then we're going to do the same thing for our second derivative. Where is this numerator 0 and where is this denominator 0 to give me the D and E case? And in the numerator, this x could be 0, and x squared minus 6 is going to be 0 at plus or minus square root of 6. And the denominator will be 0, just like this denominator was 0 at plus or minus 2. Now, I want you to think for a moment here about the domain of this function, because think about what would make sense when you're dealing with the square root, and when we're graphing, we only want to graph real numbers. We never want to be taking the square root of a negative number. So when could you potentially be taking the square root of a negative number? If x is 2, then this is going to be 0 under here. If x is 3, you'd get 4 minus 3 squared, or 4 minus 9, which is a negative 5. So if your x is bigger than 2, then this is going to become negative under here. Likewise, if x is smaller than negative 2, like negative 3 or negative 4, then you'll also get a negative. So the domain of this function right here is just between negative 2 and positive 2. Anything outside of that will end up causing us to have the square root of a negative number. So square root of 6 and minus square root of 6 is actually outside of that domain, so we don't even have to worry about those because they won't be allowed anyway, since they would give me negatives under that square root. Okay, so when I do my number lines, I'm actually going to be a little bit careful here, and I'm going to start my number line, let me use a different color here, at this domain range from negative 2 to 2. And I'm going to mark on there my critical numbers, which were those same 2 points, plus or minus 2, and then plus or minus root 2. And when I test, I just want to make sure that the test point that I pick isn't something bigger than 2 or smaller than negative 2, otherwise it won't be in my domain. So that's kind of why I stopped and started at negative 2 and 2. So for example, we need something that's smaller than negative root 2 but bigger than negative 2. So you would have to test something like negative 1.5, because square root of 2 is about 1.4. So if you tested like negative 1.5 into this derivative, negative 1.5 squared, and then multiplying that by 2 and then subtracting that from 4 is going to end up giving us, if we pull up the calculator, you can see 4 minus 2 times negative 1.5 quantity squared is negative 0.5. So that numerator is going to be negative, and this denominator is always a positive square root, so that denominator is always a plus. So this is going to be minus. If I plug in positive 1.5 into my calculator, it's going to give me exactly the same result, because this negative in front of the 1.5 will get squared away anyway. So when I do positive 1.5, this will also be minus. If we tested 0, 4 minus 0 is positive, and the bottom is positive, so this will be plus. So there's my signs for that first derivative. Now let's go and do our number line for the second derivative. I'm going to do the same thing that I did before, use negative 2 and 2 as my starting and stopping points. And here's what my second derivative formula is. That denominator is always going to be positive because we're taking a positive square root and we're making sure that we're staying within our domain. And when I cube it, it'll stay positive. So it's only the numerator that we have to worry about. And the only critical number that I have here was 0 and those 2 endpoints. So let's add 0 in there. If I test, say, negative 1, 2 times negative 1 is negative. Negative 1 squared is positive 1. 1 minus 6 will be negative, and the bottom is plus. So the whole thing altogether will be plus. If I try a positive 1, then 2 times positive 1 is plus, but this factor will still be negative. So this will stay negative. Okay? All right, so let's figure out all of our different regions. So I'm going to put in my little dashed lines here. 1 through negative root 2, 1 through 0, 1 through positive root 2. Minus signs is where I'm decreasing for that first derivative. Plus signs, which was in the middle here, are increasing. And then for the second derivative, plus signs are concave up and minus signs are concave down. And here's my 4 options. So up, down, down, up. So down here, I want to be concave up, decreasing. So that's this shape right here until I hit negative root 2 and starting at negative 2. Then between negative root 2 and 0, I'm concave up, increasing. So that's the other half of this U shape. And then from 0 to root 2, I'm concave down, increasing, which is this left piece. And then from root 2 to 2, I'm concave down, decreasing, so that's this shape until I hit 2. So putting it all together on my graph, we have negative 2 and positive 2 for my domain. We need to plot a couple of these key points. Our key points were negative root 2 for x and positive root 2 for x. Those are my critical numbers for the first derivative. And then I also had 0 for the second derivative. When x is 0 into here, this will stay 0. At root 2, you'll get root 2 times square root of 4 minus root 2 squared, which is just 2. 4 minus 2 is 2, so it's like a root 2 times a root 2, which will be a 2. So this one will be positive 2, this one will be minus 2. So we're going to get a dot that's right about here, and another dot that's down around here. And at negative 2 and positive 2, that makes this square root 0. So these are both intercepts, and we also had an intercept at 0. So drawing this shape through these 5 dots, concave up, concave up, concave down, concave down, and I don't do any arrows here because this particular graph had a domain of negative 2 to 2, so it doesn't keep going afterwards. It just starts and stops at those 2 endpoints. Okay? Okay, next example. Here we have another function with the first and second derivative already provided. So let's go ahead and find our critical numbers. So we want to find out where this numerator is 0 and where this denominator is 0 to give us that D and E case. So when does 1 minus x to the 1/3 equal to 0? If you set it equal to 0, to solve that, you would need to cube both sides. And that would just give you x on the right, and 1 cubed stays 1. So this happens when x is 1, and the denominator will be 0 when x is 0. For the denominator, or for the second derivative, we want to know when this numerator is 0 and when this denominator is 0 to give us the D and E case. So that denominator will be 0 at 0 again. And for the x to the 1/3 minus 2, if I solve that and set it to 0, I'd have to add the 2 over to the other side. And again, to get rid of a 1/3 power, you have to cube both sides. So this would just become x, and 2 cubed is 8. So this is going to give me 8. So now we're ready to draw some number lines here. And on that first derivative, we're going to draw in 0 and 1. And for the second derivative, we're going to put in 0 as well and 8, which will be way over here. So if we test a few points, and I'm not going to test every single one for you, I'll let you do some of the work here on your own. But for example, if I plugged in -1, the cube root of -1 stays -1. So this becomes 1 minus a -1, which becomes positive, times a +2. So that numerator is plus. The denominator will always be plus because we're squaring that end result. So this is going to be plus overall. If I tested a half, the cube root of a half is going to stay positive, and it's going to become something smaller than 1. So if it's smaller than 1, 1 minus something smaller is going to stay positive. So you'll get the same signs as we got for the other case. So this is going to stay plus. If we plugged in something bigger than 1, like 2, the cube root of 2 is bigger than 1, so 1 minus that will be negative. So this will stay negative. Okay, and I did that pretty quickly, but you can verify by just picking numbers and plugging them on your calculator to be a little bit more careful about it. If we do the signs for the second derivative, I'll let you verify it, but the signs that we end up with are plus to the left of 0, minus in between, and plus to the right of 8. Okay, so now if we draw in our little imaginary lines here, 1 through 0, 1 through 1, and 1 through 8. Pluses are increasing, increasing. Minuses are decreasing, decreasing. Pluses for the second derivative are concave ups, and minuses are concave downs. So here's my 4 choices. And if I look at this first piece over here, I want to be concave up increasing, so that's this shape right here until I hit 0. Then I want to be concave down increasing, which would be this shape, so I have a point of inflection right there at 0. Then I want to be concave down decreasing, which is this shape, until I hit 8. And then after 8, concave up decreasing, which is this shape right here. So I have another point of inflection at 8, and I'm going to have my arrows. So if we put this on our graph, we need a few coordinates of these important points. We had 0 as one important critical number. We had 1, and then we also had 8 for our second derivative. So plugging those in, if I plug in 0 into the original function, I'm going to get 0 right back again. If I plug in 1, I'm going to get 2 times 1 is 2, 2 minus 1 is 1. And if I plug in 8, you actually end up getting 0 back again, because you get the cube root of 8, which is 2. 2 times 2 is 4, and then the cube root of 8 is 2. 2 squared is 4, so it's 4 minus 4. So we have a 0, 0. We have a 1, 1, and then we have an 8, 0. So to the left of 0, we're rising up, concave up until we hit 0. Then we're concave down and have a little max at 1. And then we finish off this max all the way out, stretch it out till you hit 8. And then you're back to concave up again after the 8. So there's our graph. Okay, our last example. Sketch the graph of 2x plus cotangent of x on the interval 0 to pi. So we want to find out where our critical numbers are, and again, we've already got our first and second derivatives simplified for us. So let's see if we can find out where this is 0 or d and e. So to find out where it's 0, we could set this equal to 0. I'm going to bring that cosecant squared over to the other side, and I'm going to flip it around. Cosecant is the inverse or the reciprocal of sine. So this becomes sine squared x, and this becomes 1/2. And if I take the square root of both sides and throw in my plus or minus, this is the square root of 1/2 plus or minus is equal to sine of x, and that's the same as root 2 over 2. So that's going to be all of those pi over 4 angles. And if we're on the interval 0 to pi, that means we want to be just between quadrants 1 and 2. Then I'm talking about pi over 4 and 3 pi over 4. Now it is possible that this could become d and e because cosecant is 1 over sine squared. So this is like 2 minus 1 over sine squared of x, and sine of x does become 0 at 0 and pi, but fortunately we are not including those in our interval, so this actually doesn't happen because we are not allowing that to happen on this interval 0 to pi. So we don't have to worry about the d and e case, but we do have critical numbers at pi over 4 and 3 pi over 4. Now let's take a look at the second derivative. Again, I prefer not to deal with the cosecant squared and that cotangent. I'm going to change everything into sines and cosines. So this would become 2 times 1 over sine squared x times cosine x over sine of x. So this is like 2 cosine x over sine cubed of x. So where is this 0 or d and e? It would become d and e at 0 or pi, but again, that's not in our interval that we're looking at, so we don't have to worry about that. Where does cosine hit 0 between 0 and pi? It hits 0 at pi over 2. So we have that as a potential point of inflection. So we're ready to draw our number lines. Our first derivative, we're going to put pi over 4 and 3 pi over 4. And if you want, whoops, sorry about that. If you want, you can put in your 0 and your pi to tell you where to start and stop so that you don't extend outside of this interval. And then for our second derivative, we'll do the same thing. So I'm going to have pi over 2, which is right in between pi over 4 and 3 pi over 4, and then I'm going to have 0 and pi. Okay, and then if we test our signs, again, I'm going to let you do a little bit of the legwork here, but I'll show you one of them. If I wanted to pick something between 0 and pi over 4, I could test something like pi over 6. So we would need 2 minus 1 over sine squared of pi over 6, and sine of pi over 6 is a half. Squaring that becomes a fourth. 1 over a fourth becomes 4. So this is 2 minus 4, or negative 2. So this is going to be minus. Okay, so I'll let you do the legwork on that, but the signs here are minus, plus, and then minus again. For the second derivative, we get a plus and then a minus. So if we put in our little dashed lines, we want one at pi over 4, pi over 2, and 3 pi over 4. We're decreasing on these two minuses, we're increasing on the pluses, we're concave up on the pluses for the second derivative, and concave down on the minuses for the second derivative. So if we put our pieces together, here's my 4 choices. We want to be concave up decreasing. Let me give myself a little more room here. So concave up, decreasing would be this shape right here until I hit pi over 4. And then between pi over 4 and pi over 2, we're concave up increasing. So that would be this shape right here. So we have a little minimum at pi over 4. Then we're concave down increasing, which would be this shape right here. And then we are concave down decreasing, which is the other half of that little hill shape. And we're going to stop at pi, and we're going to start at 0. So let's put this on our graph. And the points that we want to be looking at here are pi over 4 for an x and 3 pi over 4 for an x. Those are my two critical numbers up here, and then pi over 2. And we're plugging those back into this original function. And to get those, I would just go ahead and use a calculator because they're going to be pretty yucky decimals. If you plug in pi over 4, it's about 2.571. If you plug in 3 pi over 4, it's about 3.7. And if you plug in pi over 2, you actually get pi. So if we plot these points, here's pi over 4, here's pi over 2, here's 3 pi over 4, and here's pi. So we're going to have pi over 4 at about a little more than 2.5. 3 pi over 4 is at about 3.7. And pi over 2 is at pi, which is about 3.1. And we want to have this shape, so we're going to be coming down into this pi over 4 to have that little min, and then we finish arcing up, and then we switch concavity at pi over 2 because we have a point of inflection. Then we arc up to that little max at 3 pi over 4, and then we finish coming down. And then to make sure that we have our graph correct, let's examine what happens at these endpoints because we only wanted to plot this between 0 and pi. Remember that cotangent is cosine of x over sine of x. So we're dividing by the sine function. And at 0, sine of 0 is 0, which is going to make this blow up. So we actually have a vertical asymptote at 0. And similarly at pi, sine of pi is also 0. So this whole fraction is going to blow up. So we have vertical asymptotes at both of these endpoints. So you can have these little dashed vertical lines, if you like, at 0 and pi. And when I draw the rest of my graph here, you can just draw your arrows arcing up or down towards that vertical asymptote. And that would finish off our graph for us. Okay? All right, this is a tough one. Concavity and the second derivative test. That concludes our video lecture. Good luck.